This is the final and formal class unit, which is an overview of 3 chapters on stars, basically their cycle, their size, and comparison. So we're not going in a lot of depth. We're going to keep it general, and you'll have a lab of sorts to do, an activity with this. After this unit, we move into basically you get to write your own lesson. Hopefully be back in class, but you'll be teaching your own lesson for about 15 to 20 minutes on anything in space and astronomy that we haven't formally learned about in class. So you get to choose the topic, you get to put together the pictures and the PowerPoint and present. But that's after this unit. This unit's going to take at least 2 weeks, maybe longer. So we'll have time. So anyway, this is the formal unit, and we're starting off with parsec. A parsec is a unit of measurement based upon, it's a distance basically. So parsec is a distance. It's longer than a light year. It's longer than 3 light years. It is what we use a lot in astronomy. You need to know the diagram, which is in the background here, and the definition. By looking at the diagram, you can pretty much tell the definition. A parsec is the distance from that imaginary pink star they drew there to the sun if, as the Earth orbits the sun, we're 1 AU away from the sun, our baseline is 1 AU, if the star appears to move 1 arc second according to the background stars in the sky. So to make that make a little more sense is a parsec is 2 words, parallax and arc second. Parallax is the apparent movement of an object as we orbit the sun. So if you say your left eyeball is the sun in winter, your right eyeball is the sun in summer, and your nasal bridge is the sun. So picture yourself orbiting the sun, your nasal bridge. So when your right eye is closed, your left eye is on one side, and when your left eye is closed and the right eye is open, you've moved to the other side of the sun. Now hold your finger out as far away as you can from your face with one eye closed. Don't move your finger, but switch eyes. Your finger appears to bounce back and forth. The finger's not moving. Your eye is going from one side to the other side of the nasal bridge. So the same thing. That's when we look at something out in space, if it appears to move with reference to the background stars, that's parallax. Move and come right back. Now, our nearest star to us, nearest star system, is the Alpha Centauri complex. And the Proxima Centauri, the closest star, appears to move less than about a 4,000th of a degree, which is split in hairs, literally very thin. But we can measure that with all our scientific tools, and we can figure out how many parsecs away that is. So parallax is the apparent movement of an object as the Earth orbits the sun. Arc second is a fraction of a degree. So in math, you found out that 360 degrees makes a circle. So if something appears to move 1 degree in the sky, it's a very slight movement. But stars are so far away, we break that down to the fractions of a degree. And if you remember your math well, a degree is broken into 60 minutes. And then each minute is broken into 60 seconds, kind of like time, just to confuse you, I guess. So 1 arc second is 1/3600th of a degree. So that's not a lot of movement. So a parsec then is the distance an object is from the Earth if it appears to only move 1 arc second as the Earth orbits. Now, you can see that that looks like a long ways away, but like I said, our closest star to us is further than a parsec away. It's 1.3 parsecs away in the diagram there. I would like for you to be able to diagram and describe, that is put in words, what a parsec is to show me you truly understand this meaning, because it's an important astronomical distance. So I put a couple different diagrams on this to show you again. The baseline is 1 AU, the distance the Earth is from the sun. As the Earth orbits the sun, the diagram below is bouncing back and forth. That little P there is your arc second. That's the angle the star appears to move with reference to the background stars. So if that's 1 arc second, then that distance would be a parsec. So like I said earlier, Proxima Centauri, that little tiny blip there, is the closest star, not the brightest, but the closest star to our solar system. And it's in the northern or the southern hemisphere, so we don't get to see it unless you go down to Australia or somewhere over there. But notice Proxima means closest to. Centauri is the closest star to our sun. Big, bold, kind of important to know. So Proxima Centauri is 1.3 parsecs from the Earth, yet we see it pretty well. Why do we see Proxima Centauri so well if it's so far away? What is there between us and these stars? Basically, there's nothing. For light to travel 4.3 light years, that is the speed of light, for 4.3 years, and not be deflected, means there is very little stuff out there in space to deflect that light. Not much molecules. I mean, the air in our atmosphere deflects the sun's light, gives us the blue sky. Otherwise, the sky would be black like on the moon. So there's not much out there in space. That's why it's called space. Reiterated. All right, Barnard star is a cool star. Back in 1997, it looked like the dot where it is labeled 1997 compared to the background stars. In 2004, it had obviously moved. So Barnard star is kind of cool because it's the second closest star to our sun at only 1.8 parsecs away, 6 light years away, but it's moving across or transversely so fast we can actually measure it. I mean, see there in 7 years, it moved quite a bit. So it moves 10 arc seconds a year. Only a few stars move even 1 arc second per year. Yet over the course of your lifetime, Barnard star will hardly move that much. I mean, figure 10 times 10 arc seconds is 100 arc seconds. That's still a slight amount. Alpha Centauri will only move 3.5 arc seconds per year. And it's the closest to us, so you'd think you'd see a lot more movement than that. Stellar motion is, we measure this in 2 ways. We cannot see 3-dimensionally. Stuff's too far away for us to see 3-dimensionally, so we see it coming towards us or away from us based upon the shift of light, like a blue shift or a red shift. If it's traveling away from us fast, then the light waves are going to be lengthened and it's going to be red shifted because red has longer wavelengths. If the light is coming, if the star is coming at us, all the spectrum, the rainbow of spectrum will be shifted more towards the blue end of the spectrum. The star will look bluer and give a blue shift because the waves are being shortened as it comes towards us. We can also measure, as we saw there in the previous slide, transverse, across the sky. I like to put my hands up in like a technical foul motion, like a referee would give on a basketball court if they get a technical foul, a T, and then slide my fingers up within each other to make like a cross, like a small T, also looks like a cross. So you can remember transverse is across the sky. So transverse, oh, I threw it in here too. Stellar motion across the sky. Where radial is our motion straight to us or away from us. That is measured on our red shift and blue shift. So radial motion, straight towards us, transverse, across. We can then use these 2 measurements to figure out exactly which way the star is moving. So the proper motion is the combination of the transverse and radial components to find out the actual movement of a star. across the sky. Spell check, turn my actual into annual movement. Okay. So those are 3 important terms to know. That one's very important to know. All right, so the magnitude scale originally was created back in the 2nd century by Greek astronomer Hipparchus. He ranked the naked eye brightness into 6 groups, with 1 being the brightest, 6 being the dimmest. That's been greatly modified since the advent of the telescope and the spectroscope and other tools. We now realize that we can see brighter things than a 1, and we can see dimmer things than a 6 because of the telescope. So like our sun, we've decided it's a negative 26.8. A negative, yeah, this is weird. It's kind of like golf. The lower you get, the better you get. So the sun's the brightest. The full moon, when it's brightest, it's a negative 12.5. Venus, pretty stinking bright. It's negative 4.4. Sirius, the dog star, is a negative 1.5. They're bright. So back when the Greeks did it, I'm sure they looked at Sirius and said, oh, that's a 1. It's a bright star. Now, they did it on stars alone. They were bright enough to realize stars twinkled. Venus, Mars, Jupiter, Saturn don't twinkle. They're planets. They didn't include their magnitude scale for planets. They just did stars. We've taken the magnitude scale to mean everything. So Hubble telescope, Keck telescope, they can see something as far as 30 magnitude, which is very, very, this is a logarithmic scale, so that's very, very weak. A 4-meter telescope can see something at 26 magnitude. Remember, the naked eye can only go to 6. So we can see stuff beyond that. Binoculars go about 10. Barnard star is a 9.5. We can't see it with the naked eye, even though it's the second closest star to us. It's just not bright enough. It's dim. But yet, it is bright enough. Naked eye limit, 6. Today we modified it as no longer limiting the whole numbers. You can see that. We put parts in there. It is apparent magnitude only. Okay, so now how bright it appears to be. So it's not actual brightness, but how bright it appears to be. It goes beyond the 1 to 6 range, which obviously you can see that. We go down to negative 26.8, which is staring straight at the sun, or way down to 26, 27, 28, very dim. A 5 magnitude change is exactly a factor of 100 apparent brightness difference. So if you're going 5 magnitudes, you've got 100 times brighter. So absolute magnitude is the apparent magnitude of all objects if they're all viewed at the same distance. So we'd say put them all at 10 parsecs away. That's absolute magnitude. It's equivalent to luminosity. Again, luminosity is like the wattage of a light bulb. How many lumens or how many watts bright is that light? So luminosity, absolute magnitude, the actual brightness. Apparent magnitude is how bright it appears to be from us, where we stand right here on Earth. So the temperatures of stars, we can use the color of the star, the wavelength, by Wien's law to determine the temperature. And Wien's law, again, is taking the wavelength, the brightest wavelength it gives. Our sun, for example, looks yellow. So it gives off that bright yellow wavelength. We take that wavelength and we take 0.29 centimeters divided by Kelvin. We can rearrange that equation to say Kelvin, the temperature in Kelvin, is equal to 0.29 centimeters divided by the wavelength. And in our sun, it comes out to be about 5,500 Kelvin. So the black-body curve is very constant. Astronomers only need to measure apparent brightness using it at as few as 2 frequency measurements. So this black-body curve, anything which can receive heat is considered a black body.